Greetings all! Welcome to this video. In this session, we are going to study multilayer perceptron, MLP. We kick off with a simple well-known example, an XOR gate, and show that XOR cannot be emulated by a single layer perceptron. Then, we introduce multilayer perceptron to address this issue. Specifically, upon completion of this video, you will be able to learn the basic notion of linear separability and the theoretical reason why XOR is not linear separable. Then I will introduce two treatments to address the XOR problem. One approach is to replace the threshold function of a single layer perceptron. The other approach is to increase the number of layers using multilayer perceptron. You need to know the pros and cons of each method. More importantly, you need to understand the representation of XOR using multilayer perceptron is not unique. There are many alternative ways based on the different decomposition of the decision boundaries. Finally, we will learn how to use multilayer perceptron composition to represent complex decision boundaries, which highlights the great potential to extend multilayer perceptron for image recognition. Before introducing the MLP perceptron model, let's first look at the Venn diagrams of the logic gates, which is an effective way of visualizing logical relations among a collection of different sets. Given two sets x1 and x2, the overlapping region in yellow, included in both x1 and x2, represents the AND gate, which is the intersection of x1 and x2. The combined region of x1 and x2 represents the OR gate, which is the union of x1 and x2. The complement of X in the universe set represents a NOT gate. A NAND gate is a NOT AND gate, whose output is 0 only if all the inputs are ones. The output of the NAND gate is complement to that of the AND gate. Thus, the Venn diagram of the NAND gate is the complement of the intersection of x1 and x2 in the universe set. An XOR gate implements an exclusive OR. Here, exclusive means XOR must contain x1 or x2, but not both, which implies that the output of the XOR gate is true if one and only one of the inputs is true. Thus, the Venn diagram of the XOR gate is the union of x1 and x2 minus their intersection. The last gate is imply. The only situation in which an implied gate output false is where the antecedent x1 is true, but the consequent x2 is false. In all other cases, the implied gate output is 1. Thus, the Venn diagram of the implied gate is the complement of the orange region in the universe set. Utilizing Venn diagrams, it is easy to show that any derived gate, such as NAND and XOR, can be rewritten using only the basic gates, AND, OR, and NOT. In particular, the following two expressions are worth noticing, which will be useful to our further discussion. The first expression is x1 NAND x2, which is equal to NOT x1 and x2. Based on the Venn diagram of the NAND gate, this expression follows immediately from the fact that the true yellow region of the NAND gate is equal to the universe set minus the intersection of x1 and x2. The second expression is about XOR, which can be expressed in terms of OR, AND, and NAND gate as follows. To validate this expression, we can see from its Venn diagram that XOR equals the union of x1 and x2 minus their intersection. Based on the set theory, we know that for two sets A and B, A minus B can be expressed as A intersects the complement of B. In our expression, B is the intersection of x1 and x2. That is the AND gate. Thus, the complement of B becomes the NAND gate. Here, the set A is the OR gate. Therefore, the above expression for the XOR gate is immediate. Next, let's look at the linear separability of a logic gate. Linear separability is an important concept in neural networks. The idea is to check whether we can separate data points in an n-dimensional space using only n-1 dimensions. For example, a two-input logic gate is said to be linearly separable if there exists a line separating the two types of data points in 2 dimensions. The AND gate is linearly separable because when we depict its 4 training data points in 2 dimensions, we can separate them using a line x1 plus x2 equals 1.5, such that the point with the green label is in 1/2 blue space, and the 3 points with red labels are in the other half space. Similarly, an OR gate is also linearly separable because we can separate its training data points using a line x1 plus x2 equals 0.5, such that 3 data points with green labels are in 1/2 blue space, and 1 red point is in the other half space. However, not all the logic gates are linearly separable. One counterexample is the XOR gate. We can see there does not exist a single line that splits the 4 input data points into 2 categories, such that the 2 green data points are in 1/2 space and the 2 red points are in the other half space. Therefore, we say XOR is linearly inseparable. For linear separable logic gates, we can train a perceptron to mimic it, and apply the perceptron learning rules to determine the weights and bias of the separate line. For example, for the AND gate, we find the blue region is x1 plus x2 greater than or equal to 1.5. By comparing this inequality with the standard form of the perceptron decision boundary, we can get the coefficients W1, W2, and B, which is 1, 1, minus 1.5, respectively. Therefore, the perceptron for the AND gate is the following. Similarly, we can train a single-layer perceptron to mimic the OR gate. The weights of the OR perceptron are all 1s, the same as the weights of the AND gate. The only difference is the biased value, which is minus 0.5. This is because the separate line of the OR gate is x1 plus x2 greater than or equal to 0.5. Since both AND and OR gates can be emulated by a single-layer perceptron, what about the XOR gate? Unfortunately, Minsky and Papin in 1969 theoretically proved it's impossible to use a single-layer perceptron to represent the XOR gate. This result is consistent with the fact that, graphically, we cannot use a single line to correctly classify the 4 data points of the XOR gate into 2 categories. To theoretically prove XOR cannot be emulated by a single-layer perceptron, let's look at its truth table row by row. In the first row, the output Y is 0, meaning that the neuron does not fire when x1 and x2 are zeros. Thus, we substitute x1 equals x2 equals 0 into this orange branch to get the following inequality. In the second row, the output y is 1, implying that the neuron will fire when x1 and x2 are 0 and 1 respectively. Plugging these values into this orange branch produces this inequality. Similarly, for the third and fourth rows, we can put x1 and x2 values into the corresponding inequality. Consequently, we can get the following 4 inequalities, which makes a system of inequalities. Next, we are ready to check the existence of W1, W2, and B for the 4 inequalities. We simplify these inequalities and get the following. From the results, we see that the second inequality implies W2 plus B is non-negative. Substituting this result into the third inequality, we get W1 is negative. Combining this result with the first inequality, we see that both B and W are negative. Thus, their sum W1 plus B is also negative, which contradicts the last inequality. Since these 4 inequalities are contradictory each other, there do not exist such solutions to W1, W2, and B. This implies that XOR cannot be represented by a single layer perceptron. To address this issue, there are 2 treatments. The first method is to replace the existing threshold function of the perceptron with a more powerful function. This method would make the existing activation function more complicated, but can guarantee that only the single-layer structure of the neural net is used for XOR representation. The second method is to increase the number of layers in the neural network. This method would increase the units and the depth of the neural net, but can guarantee the activation function of each unit is still a simple threshold function. Let's first look at method 1. Before replacing the threshold function, let's first study why it works well for the OR gate. These are the 4 data points and the decision boundary for the OR gate in 2 dimensions. In 3 dimensions, we can see that the 3 green points labeled as 1 are mapped onto the upper plane y equals 1. When the shape of the hyperplane in 3 dimensions is projected onto 2 dimensions, it looks like a step ladder, which is a Heaviside function jumping at the point 0.5. Note that the green upper plane in 3 dimensions is the result of elevating the blue region in 2 dimensions. We can translate this Heaviside function left 0.5 unit by adding a bias value minus 0.5 to the perceptron to make the threshold function zero-centered. Now let's apply the similar ideas to the XOR gate. For XOR representation, the blue region in 2 dimensions becomes band lines. Unlike the OR gate that needs to elevate the half space in 3 dimensions. In the XOR gate, we just need to elevate the blue band area, such that only the 2 green points are mapped onto the upper plane in 3 dimensions. When the shape of this hyperplane in 3 dimensions is projected onto 2 dimensions, it looks like a piecewise function whose value is 1 when x is between 0.5 and 1.5, and 0 otherwise. The single-layer neuron with this piecewise function can mimic the XOR gate. It is worth mentioning that the central idea of method 1 is to replace a simple threshold function with a more complicated piecewise function. This method has the advantage of reducing the number of nodes in the neural net, but increases the computational burden for each node due to its growing complexity of the activation function. And the learning rules for the user-defined piecewise function are unclear as well. Moreover, in neural computing, our basic philosophy is to approximate a complicated function by decomposing it into a number of simple functions, which may contradict the main idea of method 1. Thus, this approach is not practically useful. The second method for XOR representation is to increase the number of layers and nodes in the neural net, while keeping the threshold function for each node. When the number of layers for perceptrons is larger than 1, we call this neural net a multilayer perceptron. To mimic XOR with multilayer perceptron, our basic idea is to convert the blue region into the composition of several half spaces, such that each half space can be represented by a single perceptron. In this XOR example, we can observe the blue region is a band between two lines, which is the intersection of two half spaces. The first half space is the region represented by x1 plus x2 greater than or equal to 0.5. This region is the decision boundary of the OR gate. The other half space is the region x1 plus x2 less than or equal to 1.5. This region is the decision boundary of the NAND gate. The intersection of the OR gate and NAND gate makes the XOR gate. This relation is consistent with our previous expression of XOR depicted as Venn diagram. This is the Venn diagram of XOR, which is equal to the OR gate intersecting the NAND gate. Let's first take a look at the OR gate, whose decision boundary can be rewritten as x1 plus x2 minus 0.5 greater than or equal to 0. Comparing this with the standard form, we can get the weights and bands, which is a triple 1, 1 minus 0.5. This corresponds to the following perceptron for the OR gate. Similarly, the decision boundary of the NAND gate is minus x1 minus x2 plus 1.5 greater than or equal to 0. Comparing this with the standard form, the weights and bands of the NAND gate is a triple minus 1 minus 1 1.5. This produces the following perceptron for the NAND gate. We see that both perceptrons have the same inputs x1 and x2. Thus, we merge them into this neural net, whose outputs are y1 and y2. Here, y1 is the output of the OR gate, and y2 is the output of NAND gate. The intersection of y1 and y2 is the output y for the XOR gate. This intersection can be expressed as an AND gate. From the previous session, we learned that the Rojas diagram of y1 and y2 is the following, whose threshold value is 2. This is equivalent to the following perceptron representation, whose bias value is -2, and all weights are 1s. Therefore, let's merge this AND perceptron with the previous neural net, which produces the following result. This is a multi-layered perceptron which emulates the XOR gate. This solution to the XOR gate is provided by Minsky and Papert, who added a hidden layer to make a 2-layer neural network with 3 perceptron units. This unit represents the OR gate. This one is the NAND gate, and this one is the AND gate. It is important to note that this solution is not unique. There are many other multi-layer perceptrons with different weights and binds that can address the XOR problem. For example, if the first unit represents an upper left half space, and the second unit denotes a lower right half space, then their union makes the blue region, which can separate green points from red ones. Therefore, in this situation, the third unit is the OR gate, corresponding to the union operator. Alternatively, we can also construct a line with a steep slope to represent the upper right half space, and another line with a gentle slope to represent the lower left half space. The intersection of these two regions can correctly classify the green points as well. A variety of ways to solve the XOR problem indicate that a multi-layer perceptron can represent the decision boundary whose region is a polygon. To be specific, given an n-sided polygon, we can construct a multi-layer perceptron with n perceptron units representing the n sides of the polygon, respectively, in combination of AND and OR gates for assembling these half spaces together to make a polygon region. For example, to represent the following positive green region, whose boundary is a quadrilateral, we can construct a multi-layer perceptron with 4 perceptron units, denoting 4 sides of the quadrilateral respectively. For example, this side implies the following perceptron to denote this half space. This side implies this perceptron. And this side corresponds to this perceptron. The last side is associated with this perceptron. Then we combine these 4 perceptron units together with an AND gate, which produces the intersection of the 4 half spaces, that is, the green region. Thus, this multi-layer perceptron is the representation for the positive green region. The above example indicates that the perceptron can represent any polygon region through the composition of the perceptron units. Consequently, we can use the multi-layer perceptron to represent the complex decision boundaries, for example, an athlete-like shape. In this representation, the multi-layer perceptron is structured as follows. We have 2 inputs, x1 and x2, denoting the 2-dimensional data points on a plane. We first depict the head of the athlete, which has 4 sides, corresponding to the 4 perceptrons combined by an AND gate. Then, the purple arm of the athlete is a 5-sided polygon, corresponding to the 5 perceptron units, intersected by the AND gate. Similarly, we can depict the blue arm, red leg, and the orange leg of the athletes respectively. After each component is depicted, we use an OR gate to combine them together, which yields an athlete-shaped region. In this way, the multi-layer perceptron can help recognize an athlete image. Interestingly, apart from an athlete image, applying the similar ideas in a fine-grained fashion, multi-layer perceptrons can also recognize other complicated images, such as animals, digital letters, and handwritten numbers. In our lab sessions, we will see a real application of the multi-layer perceptron for digital number recognition. That's all for today's session. Thank you for your watching. Bye.